Okay, so we're going to look at cube roots of unity here. So that is, we're going to look at, let's see, t cubed minus 1 over q. And we know that this factors as t minus 1 times the third cyclotomic polynomial, t squared plus t plus 1. And so usually we'll use, remember, omega for e to the 2 pi over 3. So this further factors is not over q, but over the splitting field. Will factor as t minus omega squared over q adjoin omega. So what's the Galois group of q adjoin omega over q? Well, we've seen this already. We're really just adding in I root 3, right? So q adjoin omega is really just q adjoin I root 3, which is like q adjoin negative root negative 3. So it's a quadratic extension, so it's z mod 2. Now, if we view this as a subgroup of S3, though, how would we label our roots? Well, it doesn't matter. We pick one way. So let's go ahead and label roots like 1 corresponds to the number 1, 2 corresponds to omega, 3 corresponds to omega squared. Now, omega and omega squared are interchanged under the Galois group. So as a subgroup of S3, this is just, well, the identity permutation and the guy that sends 2 to 3 and 3 back to 2. Excuse me. So although the Galois group in this case is a subgroup of S3, it's really not, it doesn't do anything with the other root, the third root, because that was already in Q. So although it is a subgroup of S3, it's not necessarily going to be what's called a transitive subgroup or a subgroup that even uses up all the letters. It might have fixed points. And in general, that's true. If your Galois group has some roots, it's really going to be properly viewed as a subgroup of something in one less. So that's our cube roots of unity example that we've seen a bunch. Let's look at the fifth roots of unity that we saw already as well. We worked out what the Galois group was. Let's look at, let me say, fifth roots of unity. All right, so let's let zeta to the fifth be 1. And, well, let me just say what zeta is. Zeta is e to the 2 pi I over 5. And this is a 0 of the irreducible polynomial t to the fourth plus t cubed plus t squared plus t plus 1. And we already worked out what the Galois group was, right? So let's let G be the Galois group of q adjoin zeta over q. Then for every integer between 1 and 4, there is an element that took zeta to zeta to the I, for I is 1, 2, 3, 4. So sigma that, then G is, of course, just sigma 1. The guy that takes zeta to zeta is, of course, the identity. And we have sigma 2, sigma 3, sigma 4. And let's just notice something real quick here. Let's do sigma 2 twice. So we do it once. Zeta is going to go to zeta squared. Actually, let's do it twice first. And then what's going to happen next? Well, it's going to send, sigma 2 is going to send zeta squared to wherever it sends zeta squared. So that's going to go to zeta squared squared, which is zeta to the fourth. Okay, great. Let's do sigma 2 3 times now. Well, I already know what happens when we do it twice. We get, what did we say? We got zeta to the fourth. All right, so let's do sigma 2 one more time. Let's see, sigma 2 sends zeta to zeta squared, and then we're going to take that to the fourth. So I think that's zeta to the eighth, which is zeta cubed. All right, let's do it one more time. So that's just going to be sigma 2 on whatever we just got. All right, so we're going to square whatever we just got. That's just zeta back. Okay, so sigma 2 to the fourth is the identity. It doesn't move zeta around. Sigma 2 squared is the guy that takes zeta and spits out zeta to the fourth. Sigma 2 squared is that one. Sigma 4. Sigma 2 cubed is the one that takes zeta and cubes it. That's this one. And of course, we're back here at the fourth. So this group is actually generated by sigma 2. And sigma 2 has order 4, so it's Z mod 4. Okay, so let's take a minute and let's work out the Galois correspondence here. So let's do the Galois correspondence. So let's write out our subgroups. There's, of course, the trivial group. There's, of course, the whole Galois group. And let's go up to Z mod 4 for a second. Z mod 4 has 3 subgroups. The trivial, any cyclic group has as many subgroups as divisors. 4 has 3 divisors, 1, 2, and 4. So the subgroup generated by sigma 2 squared is going to be an order 2 subgroup there, right? Because if we do sigma 2 squared twice, with sigma 2 to the fourth, we're back at the identity. So our last group is going to be, let's see, let me just make sure I call it what they call it in the book. Let's let I be the trivial group. So that just has the identity in it. We have all of G, and then in the book they call A the group that's generated by sigma 2 squared. So there's those 3 guys, and that's it. And we actually had you already work out what the fixed field was for A. So F itself, we have, of course, Q. We have Q adjoin zeta, the whole field. Those are always in F, the field you're extending and the extension. And then we had this weird field, which was Q adjoin zeta plus zeta to the fourth, which you found in homework 11 or 10, I forget. But there was this last guy. And if we apply sigma 2 squared to zeta plus zeta to the fourth, let's just see that it fixes that element. What is that? Let's see. Sigma 2 squared, I think we computed this. It sent zeta to the fourth. And so let's see, that's going to go, it breaks up under addition. And then this zeta, this fourth power comes out. Zeta is going to go to zeta to the fourth for each of these. And then 4, this is going to be the 16th. And then 16 mod 5 is 1. Okay. So it fixes that. All right, cool. So A dagger is this one. Let's see, identity dagger. Identity fixes everything. So that's everything. G fixes nothing because it sends all of the zetas. It fixes only the rationals because it sends zeta to every possible power and it cycles through all of them. And then this subgroup A is the fixed field that it corresponds to is this guy here that you found in your homework. Okay. So this is the Galois correspondence for this 5th roots of unity example that we saw 2 chapters ago.